Okay, so we're going to do a video about interpreting regression results, because I've already got a video out there about using Excel to run regressions, but after you do that, you want to know, well, now what do I do with this stuff? So we wanted to use gas consumption as our dependent variable. Independent variable, we'll just go ahead and use all of them. So I'll highlight all of those and scroll down. I highlighted the first row, so I want to say that's my labels. I don't have any perception that the intercept should be 0. I'm going to keep my output on this page, so I'll tell it to go right there. Don't know if this is going to hit any of you on this screen over here. So I'll do what I did before and kind of get rid of some of the cells that we don't really need to talk about at this point. I'll get rid of those. That might throw people off though, but okay. We don't really talk about standard errors either. So I get these results, and I think, well, in the video I showed what the equation would look like. So I could do, I'll just write it out again. So here was our equation, and I played around in the other video about coming up with estimates for gas consumption if you knew particular values of some of these variables. So I think I said, you know, if you think that the gas tax is 8 cents, and if you think the average income is so many dollars. So that other video will tell you about that. But we want to know we want to talk about how to interpret these sorts of results. That this is a decent equation to hang my hat on. So, because again, Excel is going to spit out results anytime you anytime you give it data. It's going to try to come up with some sort of best fitting line. It's going to come up with an intercept and coefficient values for anything that you throw at it. So whether that equation is good or not, whether the independent variables explain anything about the dependent variable, it just sees this table as a table of numbers, and it knows to do these calculations to come up with these kinds of results and spit it into a table like this. So it's kind of up to us to be able to look at these things and say, well, is this a good equation or not? You can think about the equation overall. So how good does this entire set of independent variables do in explaining the dependent variable? So that's what the R squared and adjusted R squared are for. So I look at my adjusted R squared, my R squared, and this gives me a sense of how well all of these independent variables do in explaining the variation in gas consumption. So it doesn't really tell me, the R squared, the adjusted R squared, doesn't tell me about individual variables per se. It just says of this group that you've picked, they do, you know, this well at explaining gas consumption. So in this case, it looks like, you know, 65, 68% of the variation in gasoline consumption is explained by these 4 variables that we've picked. So again, the R squared, the adjusted R squared, it's not able to tell me just in those 2 statistics. It's not able to tell me, well, how well did the gas tax variable do? How well did the paved highways variable do? It just says of these 4 that you picked, then they explain, again, 65, 67% of the variation in gas consumption. So there's 30-something% of the variation in gas consumption that is not explained, that maybe if you had other variables, they'd be able to add some explanatory power to it. If this set of variables is a good set of variables to use, well, again, it's explaining 67-ish%, which I don't know if I went into the distinction between cross-sectional data and time series data. But, you know, this does a decent job. If you're trying to explain how many millions of gasoline that people are consuming, to explain 67, you know, 2/3 of it with just 4 variables is pretty decent in my mind. I don't know where I got this from, but it was in undergrad when I took my econometrics class. The kind of rule of thumb that I was told was if you're using cross-sectional data and you get an R squared about 0.3 or 30% or better, then you're doing a decent enough job. That's just sort of the rule of thumb that I was taught, and it seemed to do a decent job. But again, if you're explaining 2/3 of the variation in gas consumption with just these 4 variables, then that's pretty good. So again, the R squared, just R squared, explains the overall set of independent variables that you have. And I think I mentioned before too that one of the characteristics of R squared is that if you add variables to your model, it never decreases. So you could be, and was that this class where I did the the first letter of the car prices, and I did the first letter of the car. I think that was this class. And I included a variable on the first letter of the car's name. And that shouldn't obviously have any effect on the car's price, but it actually made the R squared go up a little bit, or at least it didn't make it go down. So if you ran a regression with that variable in there, you might think, well, the R squared didn't change, or the R squared may have actually increased. So it must be, including that first letter variable must be a good thing to do. But again, conceptually, theoretically, that's kind of ridiculous. So you can look at the R squared. It's somewhat helpful. The adjusted R squared does what it says. It adjusts the measure of R squared for including additional variables, some of which may not be helpful. So I think when we looked at the adjusted R squared, after we added that first letter variable, it actually went down, which is a hint that adding that variable didn't improve anything to the explanatory power of the entire model or the entire equation. So anyway, again, the R squared, the adjusted R squared, tells us about the set of independent variables that you picked, and it did a pretty good job. That's a separate question from asking about, well, how does each individual variable do in explaining gasoline consumption? So that's where you want to look at the coefficients and the standard error, but that leads you into the t-statistic and the p-values. So first off, the coefficients, the signs of the coefficients are things that we want to look at, because we expect that, we're including these independent variables because I think that gasoline tax has an impact on gasoline consumption. I think that average income has an impact on gasoline consumption. So the first thing that we want to think about is, well, in what direction do I think that impact is going to have? If the gas tax increases, do I think that's going to increase or decrease gas consumption? If the average income increases, do I think that will increase or decrease gas consumption? So you can come up with guesses beforehand, and I would presume that, well, if the gas tax goes up, then that's an increase in the price of gasoline, and that should reduce people's gasoline consumption. So to me, seeing a negative sign on the gas tax coefficient makes sense. Incidentally, these coefficients, they're basically, well, I would say they're like partial derivatives. When I see this coefficient, this value or this sign here presumes that the question that it answers is, what happens to gas consumption if there's a change in gas tax, holding all of the other variables constant. So if I were to keep average income and paved highways and proportion of the population constant, and I increased gas tax, then it would decrease the gas consumption by 34 or whatever. So it always presumes that you're holding all of the other variables constant, and so this would be the effect on gas consumption of changing the gasoline tax. So it's negative, which is good. The portion of the population with a driver's license, well, I would presume that if more people have a driver's license, then there should be more gas consumption. So when I see there's a positive coefficient there, then that makes sense to me. That's good. And a bunch of you mentioned, too, that, well, you would have thought that when incomes go up, people should consume more gas, because we would presume that gas is a normal good, that gasoline consumption is a normal good. We do see that its coefficient is negative, so that's a little weird. So that when people's incomes go up, that's associated with less gas consumed. There's some ways you could, I guess not explain it away, but there's some ways you could explain it, I guess. Maybe if people's incomes are low, they're buying more used cars, and they're buying more, junker cars that don't have as good fuel efficiency. And when your income goes up, maybe you're buying newer cars where the mileage is better, or maybe you're even buying electric cars or hybrids or something like that. So there's some ways you kind of wave your hands and explain that negative coefficient, even though it's kind of surprising when I first look at it. The amount of paved highways, if that increases, then I guess there's a reduction in gas consumption. You probably have some routes around your house that are like this. You're kind of like, man, I wish there was a highway connecting, my house to this other place I go to all the time, instead of having to take all these back roads or these, surface city streets where you're having to stop and go a lot more, and maybe that ends up consuming a lot more gas. So the more highways there are, then maybe it reduces your gas consumption because you don't have to stop as much. So again, I wouldn't necessarily have presumed that the coefficient on paved highways was going to be negative, but I could explain it away if I had to. One thing to look at is the signs of these coefficients, whether those make sense. You could look at the magnitudes of these coefficients, and these end up being a little harder. You have to really kind of pay attention to what your data, what units your data is in, to make sense of these, because the coefficients are going to tell me what happens to gas consumption if there's a 1 unit change in any of these independent variables. So my gas tax, well, it was the gas tax, but it was also measured in cents per gallon. So what this coefficient tells me is that if there's an increase in the gas tax by 1, in this case 1 cent per gallon, then what's going to happen is that the consumption of gas is going to fall by 34.8 million gallons. So you have to be, again, to be able to interpret these as far as the magnitudes go, or the sizes of these things go, you have to be kind of careful, because you might look at these and go, well, look, the proportion variable had the biggest coefficient. That must mean it's the most important, because it was 1336. That's a lot bigger than the average income. That thing was only 0.06. So it must be that the proportion of the population with a driver's license is way more important than average income, because its coefficient is bigger. Well, it's only like that because of the units that all of this data is measured in. So the proportion of the population with a driver's license, that's in percentages. And that would be a little weird, because if I were to increase this variable by 1 unit, then I would get a change in the consumption of gas by this many millions of gallons. But since this is a proportion, since these are all less than 1, I can't ever really increase it by 1 unit. I can't go from like 52.5% to 152.5%. So again, all these things make it so that you have to be really careful in interpreting the magnitudes of these coefficients. But after you've done that, then you want to know, well, again, is the gas tax an important variable in affecting gasoline consumption? Well, I know that it's got the correct sign, the sign that I expected, and the size of the variable, I guess, maybe makes sense. If there's an increase of 1 cent per gallon of a gas tax, that reduces gas consumption by 34.8 million gallons, maybe. But is this important? Excel is always going to spit out a coefficient for you. It's got these numbers and it's got these calculations. It's always going to give you a value for the coefficient. It's never just going to give you like a 0 with a star by it saying, like, no, don't worry about this variable. This isn't important. It's just going to give you some variable. You want to know whether it's important or not. The p-value essentially is, if the quickest way of figuring it out, is looking at the p-values. Because again, the p-value is the probability that the effect of the independent variable on the dependent variable is 0. So again, the p-value tells you the probability that the effect of the particular independent variable on the dependent variable is 0. So if you have a high p-value, I guess I should write this out too. High p-value means high probability that the effect of the independent variable is 0. A high p-value basically tells me that the effect of the independent variable on the dependent variable is 0. So when I look at my paved highways here, I say, well, that's like 48%. So there's almost a 50-50 chance that the effect of paved highways on gasoline consumption is 0. Or there's almost a 50% chance that paved highways has no effect on gas consumption. So it's, again, what you're really looking for, if you're trying to look for variables that are important or that do have an effect on your dependent variable, then you want to look for low p-values. Here I see that this paved highways is pretty high. So I'll write this out too. 47.8% chance that highways has no effect. And you might even think like, well, that's less than half. But again, we're doing statistics, and people might be driving on these highways. People might be consuming their gas based on the results of our study. So you wouldn't necessarily want to be like, yeah, it's a 50-50 chance that what I told you is bunk. So we usually are pretty strict in terms of the size of the p-values that we're looking for, that we consider to be important. So again, if there's a 47.8% chance that paved highways has no effect on gas consumption, then we would say, well, it seems like the paved highways variable is insignificant. There's no effect. Insignificant. My other ones, though, my gas tax, well, there's only a 1% chance of that. I'll say gas tax has no effect. So we would call it a significant variable. Average income is even less than that, so even more significant. And this one is even more because it looks like it's 1.5, but this is actually 1, 2, 3, 4, 5, 6, 7. So that p-value is tiny, so even more significant. So the only variable here that I included that seemed to not have a significant effect on gas consumption was the paved highways. The rest of them seem to be significant, at least the 1% level. You have to be careful with how we word these things. When I say they're significant, there's a difference between something being significant and being important. I know that might just sound like a nomenclature sort of thing, but in statistical terms, when I say that this gas tax variable is significant, that means that I have a strong probability that the effect of gas tax on gas consumption is what is measured here in this coefficient. So I should have a 99% confidence that the effect of gas tax on gas consumption is this 34.8, negative 34.8. For the paved highways one, it's like, well, it looks like the effect of paved highways and gas consumption was 0.002, but really there's a 53% chance that the effect is 0, that it has no effect at all. Again, when I say that the gas tax variable is significant, that just means that I should have a lot of confidence in the value of the coefficient that Excel estimated for me. I can be confident that the measured effect of the gas tax on gas consumption is, as it says here, 34.8. I can have a strong confidence that the effect of average income on gas consumption is 0.06. It may be just by the size of these variables that the gas tax is more important. Again, a lot of that just kind of depends on the units that you measure these things in. It's not a minor topic, this distinction between significance and importance, but it might be a little more than we need to worry about as far as this class goes. So again, the individual t-statistics, p-values, give you a sense of the effect of individual independent variables have on the dependent variable. And so what some people might do is they say, well, the paved highways end up looking like it was insignificant, so maybe I should run another regression and just not include that one. You could try that. I'm not a huge fan of doing that sort of thing because, again, this was from my undergrad class also, but they said really what should drive your models, what should drive your choice of independent variables is what you think is theoretically important. So if you have a sense that paved highways should be important in gasoline consumption, then I would include it, continue to include it, even though it shows up as insignificant. You can just say, I thought this was kind of unexpected, but I still think there's a good reason to include this. Maybe this was just a weird set of variables that I included, or a weird time frame for when I collected this data, when the data was collected. So I tend to not be a big fan of just arbitrarily deleting variables to make your results look better. I always like including the variables that you think are theoretically important. I don't know much more I could say about that. Let's see. Is the adjusted R squared always a better indicator than R squared? Again, I tend to like it more if you have more than one independent variable, because again, it helps to correct for the addition of new variables. A lot of times, academic articles will include both. People will include both measures in there. And I guess as long as you can remember that adding more variables is never going to make your R squared go down, if you kind of remember that little weird fluke about it, and not let it, sway you one way or the other, then it's not bad to include it as well as including the adjusted R squared. And then, does the intercepts t-statistic and p-value have any significance? It can in certain situations. Not for this particular model where we're trying to explain gasoline consumption. I mean, what it's telling me is that if there was no gas tax, if people's average income was 0, if there was no paved highways, and if none of the population had a driver's license, if all those variables were 0, then gasoline consumption would still be 377.3 million gallons. So I don't exactly know what that means in the context of this particular regression that we're running. Later on, though, let's see. We're going to be looking at production functions and cost functions. Oh, let's see. We're going to have graphs where I predict, or I have a sense that there should be some intercept, some non-zero intercept, so it should hit the y-axis at a particular point. And so I would have a guess for an intercept in mind, and I might, in that case, I might want to look at the t-stat and the p-value to see whether the estimated coefficient or the estimated intercept is what I expect it to be. So there are particular situations where you want to look at it. A lot of times the intercept also is going to sort of be the kitchen sink for all the other variables that you didn't include. There's a lot of other variables that are going to affect gasoline consumption besides the 4 that I picked here. And so what Excel does is all those other things that it can't explain, it just kind of tosses into the intercept term. And so for a model like this, I might look at it, it's kind of interesting, 377, but I wouldn't necessarily lose any sleep whether it showed up as being significant or not. Well, we have to compare between each model. What statistic do you use when comparing different models? Okay. So Colleen asked about comparing different models. If I did another regression with those, and I'll skip the proportion with the driver's license, and I gotta put this result down here maybe, and hit OK. And again, let me get rid of some of these other. So I've got these results. I dropped my proportion of the population with a driver's license variable. And if you're asking particularly about, we have to compare between each model. Again, the R squared is going to be, the R squared, the adjusted R squared, those are going to be the statistics that give you a sense of how well your entire model does. So from this first model, I went from an R squared of 0.65, 0.67 to this one where I dropped only one variable, and it dropped down to 0.3. So I went from explaining almost 65% of the variation in gas consumption to only explaining 30% of the variation in gas consumption. So that proportion of population variables seem to be pretty important. So that would be a pretty big giveaway that if the R squared is, whenever the R squared is higher, then it usually means that the variables that you pick did a better job of explaining the variation in the dependent variable. So here I'm only explaining 30% with these 3 variables that I have, whereas before I had 67% with the 4 variables that I picked before. I can also see that as I do that, before my my gas tax was significant, and it still is. My average income, its p-value was pretty small, and it actually, in this model, actually went up a bit. So usually we say, well, you can talk about things being significant at the 10% level, and so if your p-value is less than 10%, well, you could still say that it's significant. And so in this case, the average income variable still is significant at the 10% level. But before it was really small. I mean, in the first model, it was significant at the 1% level because it was tiny. Here, it would not be significant at the 1% level. Same thing with the paved highway. Let's see. Oh no, look what happened to paved highways. Paved highways went from being insignificant to now being significant. So that was odd too. If you drop variables, I'll say it that way, if you drop variables, then Excel is going to try to figure out, well, of the variables that are here now, how can I explain gas consumption given the 3 independent variables that I have? And so in this case, it must be thinking that paved highways is important now because it's considering its p-value to be significant. So it's kind of interesting because you might have thought, if you ran these regressions the opposite way, if you just picked these 3 variables first and ran it, then you might say, oh, look, 30%, he told me that his undergrad class said a 30% R squared was good. And all those p-values are significant at the 10% level. So, looks good. I'll just report this and watch TV because I got a good results here. And if you would have stuck around and run this other model, your R squared would have shot up. You would have seen that, well, actually, the paved highways wasn't significant. But including that variable that I didn't have before, that was very important. Again, comparing these different models, just the way you asked the question first, Colleen, I would have said, well, just look at your R squared or your adjusted R squared. That's probably the quickest way to compare 2 models. But you can also get a little more, nuts and bolts of it and figure out, well, do I still get the signs of the coefficients that make sense? Do I still get the p-values that I thought? So depending on the level of specificity that you want, that would probably be how I would answer it.